Hello, I am Tony Truelove, and I will be your moderator for today. Welcome to the third in our Engage the Experts webinar series. This series will give you more insight into diesel cylinder deactivation, which is a key to achieving future diesel emissions. Each webinar will delve into various aspects of CDA. Our experts will be available to take your questions, so feel free to send us a question through the Q&A function as you're listening to our presentations. So this week's webinar is entitled The Advantages of CDA in Real-World Drive Cycles. Our experts will discuss how the benefits of cylinder deactivation was proven over real-world drive cycles. The presentation is based on the SAE technical paper, The Advantages of Real-World Drive Cycles, and it is SAE paper, apologize here. The SAE paper is 2018-01-0880, Diesel Engine Cylinder Deactivation for Improved System Performance over Transient Real-World Drive Cycles. This paper can be purchased through SAE if you want all of the details. Now I'd like to introduce you to our experts. Dr. Greg Shaver is a professor at the University of Purdue University, sorry. Greg has been working with Eaton and Cummins for several years. And he is focused on creating challenging and interesting, relevant career-launching research. His efforts are well known in the industry and regulatory agencies, including the US EPA and California Air Resources Board. And Greg joined the Purdue faculty in 2006. Greg, what were your main takeaways from this research?
Yeah, thank you very much, Tony. At Purdue, we've been exploring and studying, researching the benefits or potential benefits of valve train flexibility and cylinder deactivation since about 2008. So we've looked at a number of different strategies to improve the efficiency of the diesel engine system. And as our audience, I'm sure, is well aware, one of the challenges is getting the after treatment hot and keeping it hot, and trying to do that in such a way that we continue to operate the whole system as efficiently as possible. So we've developed a number of strategies to maintain the temperature of the after treatment while improving fuel efficiency. And one of the most impressive such strategies is cylinder deactivation. So we're going to be talking about that today. We've also done work focusing on using valve train flexibility in a diesel engine to increase the temperature of the after treatment. That'll have to be subject matter for another day. But the benefits of cylinder deactivation are significant. As you'll hear today, a very good strategy at low to moderate loads for not only increasing the temperature of the after treatment or maintaining the after treatment of the temperature, but also generating lower engine out Knox and soot emissions, at least in our study. So you save fuel, you increase temperature coming out of the engine, and you reduce the engine out Knox and soot emissions. All of these things are consistent with an improvement in what's typically considered a trade-off between criterion emission pollutants and fuel efficiency. So we can make improvements across the board with cylinder deactivation. And our study has also explored other strategies for trying to do likewise. And the reason to do that is to understand or to make sure we weren't fixated on one particular technology. So we explored internal EGR by way of exhaust reinduction, exhaust trapping. We looked at other ways to reduce the airflow coming through the engine, including some more exotic gas exchange strategies. We looked at early exhaust valve opening. We looked at a lot of things, but probably just about everything. And I think we, in fact, invented some new strategies for reducing the airflow through the engine. Of all those techniques, cylinder deactivation did as well or better. So it is, I hope, a prime path moving forward for the industry, and I'm excited about the work they'll hear about today. Thank you.
Great, thanks. Our next panelist is Dr. Jim McCarthy, and Jim is the Chief Engineer for Vehicle Technologies and Innovation at Eaton. Prior to joining Eaton, Jim worked at Detroit Diesel. He holds a PhD, a Master's of Science, and Bachelor's of Science in Mechanical Engineering from Purdue. So we've got a staff full of Boilermakers here, it looks like. So Jim, what, in your opinion, what were the most significant parts of this research paper?
Thank you, Tony. Yeah, this was an exciting collaboration where we teamed up with Purdue and Cummins for about 7 years. And the camless valve train on the Purdue engine was a key research lever such that we could determine the merits of variable valve actuation on state-of-the-art engine and aft treatment systems. And Greg just gave you an example of all the different variable valve actuation techniques that were tried. Cylinder deactivation proved to be a significant technology for both saving fuel while increasing SCR temperatures for improved NOx reduction. Today's presentation was significant as it quantified the benefits of CDA over key drive cycles, showing impressive fuel savings. We had a team approach in our collaboration with Purdue students and Cummins, which made this project for me very enjoyable. I really look forward to Mirinal's talk today. Thanks, Tony.
Thank you, Jim. And our special guest speaker is Dr. John Johnson. He's Professor Emeritus at Michigan Tech University. He is a fellow of the SAE International and American Society of Mechanical Engineers. And Dr. Johnson is an expert in the field of diesel engines, and his experience spans a wide range of analysis and experimental work related to advanced engine concepts, emission studies, fuel systems, engine simulation, and exhaust aftertreatment system. Welcome, Dr. Johnson. Would you please share a few words with us?
More than happy to do that. I want to tell you about the award that this paper received in April of 2019. The name of the award committee is SAE John Johnson Award Committee for Outstanding Diesel Engine Research. In 2007, since I had about over 125 graduate students out in the industry and in universities, I thought it would be good to have a nice award, a prestigious award. So I started working with the SAE staff, and ultimately the committee was formed. And there are actually 2 awards, which I'll touch on in the end. And this first one is the paper award. And first I want to go over the committee. Kirby Baumgart from John Deere. Kirby was one of my graduate students in the 1990s. And the second member is Cornelius Opris. Cornelius worked first for Caterpillar, and more recently he's been at FCA, and he was also one of my graduate students in the 1990s. Dave Marion, who's retired from DDC. Dave and I first got working together on the early emissions in CRC and also in SAE and EMA in 1968 when I was working at International Harvester and getting in on the early development of the first standards for heavy-duty vehicles for California. John Wall, I knew John when he worked at Chevron and also all the time at Cummins. We've had a lot of research money from Cummins, and so John and I have been colleagues over many, many years. Nick Chernansky from Drexel University, I met in the early 1980s when I worked with him on a National Academy's committee on diesels in light-duty vehicles during the fuel economy concerns. Ron Graves is retired from Oak Ridge National Laboratory. Ron and I worked on several National Academy committees, and the last one is Dean Tomasek from FEV. I've had interactions with FEV over the years, and I think this is a very prestigious committee, and that's what helps making it a prestigious award. The next slide, typically there's over 100 to 150 papers. It varies from year to year, and we look back a year in case of this award between August of 2017 to September 1 of 2018, from various technical meetings and also the two journals, the Fuels and Lubricants and the Engine journals. Two members of the committee, actually John Wall and Nick Chernansky, have the job of trimming these number of papers down to 8, and then the whole committee reads these and has a form to rank the various papers. And so this paper is very prestigious, I think. The next slide, so there's the Best Paper Award, which this paper received, and so that the individual medal is the other thing that's given every year, and it is based on the contributions and leadership in diesel engine research. And Alexis Yesserts of Cummins received the award in 2019, in April of 2019. I would just like to offer a few other observations. I've worked probably more in the area of after-treatment systems and modeling. And in order to develop technologies for low NOx standards for California and nationally, there is really a need to also focus on the after-treatment systems that are efficient for real-world driving and getting emissions and fuel consumption, and coupling them with the technologies such as the CDA. I think from our research we need more than a 99% NOx control efficiency, so the engine thermal efficiency can be high. And on June 23rd of 2020, from our research, we were granted a patent for an ultra-low NOx emission system, which appears to be more applicable in the near term for light-duty vehicles. We have found in the literature that VW and BMW have systems now that approach our system, but without a second DOC, which our system has. So with that, I'd like to thank you, and hopefully if you have questions afterwards, I'd be glad to answer them.
Thanks, John. And we definitely look forward to having you join us a little later on for the Q&A section. And our keynote speaker is Dr. Mrinal Joshi. And Dr. Joshi is a systems engineer at Cummins. She holds a doctorate in mechanical engineering from Purdue. Her research work at Purdue focused on improving fuel efficiency and reducing emissions using valve train flexibility in a diesel engine. As a result of this work, she has authored 3 journal papers and 1 conference paper, and has co-authored several more journal papers. Her career interests include XEV powertrain modeling and controls for improved performance. Dr. Joshi, take it away.
Okay, thank you very much, Tony. So good morning, everyone, and thank you all for joining this webinar. I'm really excited to present today. The title of my presentation is Advantages of CDA over Real-World Drive Cycles. This work is a part of a larger body of work carried out at Purdue under the guidance of Professor Greg Shaver, and with Cummins and Eaton as our research sponsors. So I want to take a moment, and I want to sincerely thank Dr. Shaver for enabling this work and for his guidance. I also want to thank my former Purdue colleagues and co-authors on this paper. It has been a really fun experience to work with Dr. Shaver. The topic for today fits in well with the theme that the webinar series has brought up so far. So today we'll look at how cylinder deactivation can be used in a medium-duty 6.7-liter diesel engine to reduce greenhouse gas emissions and also have other advantages. So with the overview, I'll start out with the introduction. We'll take a look at the experimental setup at Purdue, followed by a discussion of results of CDA at steady-state idle, where we see that it has sufficient temperatures and sufficiently low exhaust flow rates to allow a slower cool down of the after-treatment system. And then we'll move on to some results over the transient drive cycles. So the first result that we look at is over the FTP, where we have demonstrated experimentally that CDA can reduce fuel consumption by up to 3.4% while maintaining similar tailpipe out NOx. Next, we've also predicted results over the Orange County bus cycle. So this cycle was developed by the West Virginia University, and we used it for our simulation to study CDA. And over this cycle also, CDA is predicted to have about 5.6% lower fuel consumption when compared to the state-of-the-art thermal management. I think the most attractive results we have predicted so far is on the Enrail Portrail cycle. So on this cycle, the CDA is predicted to have up to 35% lower fuel consumption. And the key feature that all these three drive cycles share in common is large amount of operation at or below 3 bar BMEP, that is low to moderate loads. That presents lots of opportunities to run CDA as an alternative to maintain after-treatment temperatures and reduce CO2 emissions. So this is a picture of the experimental setup at Herrick Labs. We have an inline 6-cylinder Cummins diesel engine, which is camless, and this engine meets 2010 emission standards. It is equipped with a VGT, a CAC, and external high-pressure EGR, which are factors in enabling it to meet those emission standards. I think the star of this experimental setup is the electro-hydraulically actuated variable valve actuation system. So this system is controlled via a D-space controller, and it gives us complete flexibility to control valve motion in a cylinder-to-cylinder specific manner, even cycle-to-cycle specific manner. Cylinder deactivation has been one of the strategies that VVA has enabled, and like Dr. Shiver mentioned earlier, several other strategies have also been studied, for example, IVC modulation and exhaust valve modulation. And there are publications available from Purdue which look at those closer. The test cell is also equipped with a 2010 compliant after-treatment system, so we have a DOC, DPF, and the SCR, as you can see in the picture. That allows us to study the effects of our engine strategies on the after-treatment temperatures. We also have an AC dyno installed in the test cell, and that really helps us to run transient drive cycles, like the results that we see today. So the next is, let's have a quick look at the HDFTP, which I'm sure all of us are very familiar with this as the drive cycle that EPA uses for certification of medium and heavy duty on-road engines. So the key salient feature of this drive cycle is, again, the significant amount of time which is spent at the loaded idle condition, which for our engine was 800 RPM and 1.3 bar VMEP. So about 43% of the drive cycle time is spent at this condition, and it accounts for 5% of the total fuel spent at this condition. That brings us to the motivation for this study, which is thermal management at low loads. So as you can see from the plot at the bottom right, SCR NOx conversion efficiency is highly dependent on SCR temperatures. And ideally, it needs temperatures more than 200 C, preferably about 250 C, to have high conversion efficiencies. As shown by the plot on the bottom left here, we see exhaust temperatures for this engine over its operating speed and load map. So below loads of about 3 bar BMEP, the exhaust is hardly above 220 C, which means that it is too cold to enable the after-treatment system to reach those high conversion efficiencies. This is just at engine outlet, which means by the time it reaches the SCR, we'll have heat losses and the temperatures would certainly be a tad lower. As a result of this challenge of firstly getting the after-treatment to those temperatures and then maintaining it there, engines will typically use strategies like delayed in-cylinder injections, HC fuel dosing, or exhaust throttling, or some combination of these to get the after-treatment to temperatures and to maintain it there. Here's some results of SCR outlet temperatures over the HDFTP, which have been experimentally obtained, and these correspond to the baseline operation. And if I tack on the state-of-the-art thermal management operation here, we see a clear difference immediately. So the baseline operation has lower temperatures and it is not suitable for a fast warm-up or for a stay warm operation. But the state-of-the-art thermal management is a strategy that uses one of the techniques that I talked about earlier to elevate exhaust temperatures to enable faster after-treatment warm-up. As a result of using delayed in-cylinder injections and other techniques, the state-of-the-art thermal management calibration has lower engine-out Knox also. So along with this, combined with its higher SCR outlet temperatures, allows it to meet 2010 emission targets. So this is the calibration that the engine would use for most of its operation throughout the day to maintain temperatures and meet favorable Knox at the tailpipe. If we translate this on a fuel consumption versus tailpipe out Knox scale plot, we see a plot that looks like this. On the x-axis, we have the percentage change in fuel consumption normalized with respect to the baseline operation, which is the black dot here. So before I proceed on to this, I want to quickly explain the Y label here, which says normalized cumulative predicted tailpipe out Knox. So the after-treatment system for these experiments was not set up for active dosing. Therefore, we used SCR outlet temperatures along with the SCR Knox efficiency curve to predict a tailpipe out Knox by using engine out Knox measurement. So that is why the word predicted tailpipe out Knox shows up here. So as we see from this plot, the state-of-the-art thermal management has 35% lower Knox than baseline, and it gets there by using 5% more fuel, allowing it to meet 2010 emission standards. So an engine would keep doing that, keep using this strategy, and keep inculcating more and more fuel consumption. The favorable direction that we all want to get to with the target of reducing greenhouse gas emissions is to the left. That is with lower fuel consumption and with similar and or lower engine out Knox. And this is where CDA is a very helpful strategy. So next, I'm going to talk about some steady state results at CDA. On this slide, let's start out with the cartoons on the left here. They just show how CDA was achieved for our experiments. We deactivated 3 of the 6 cylinders by first cutting fuel and then by cutting valves to those cylinders. The transition into and out of CDA was very smooth, just on the side. So on the left, on the right here, we have a PV diagram which shows in-cylinder pressure versus log volume traces for the baseline operation, for the state-of-the-art thermal management, and for the 3-cylinder CDA operation. So notice how the state-of-the-art thermal management has the highest exhaust pressure amongst these strategies, and it deliberately uses that elevated exhaust manifold pressure in order to reach temperatures for fast SCR warm-up. 3-cylinder CDA has the smallest pumping loop among these 3 strategies. It's a very non-discernible, but it's very small. And that is one of the key reasons, that 3-cylinder CDA allows us to save fuel. So reduction in airflow as a result of cutting 3 cylinders, and then there's a smaller pumping loop, and there's a lower fuel consumption. These are all experimental results at 800 RPM and 1.3 bar VMAP steady state. On this slide, on the first plot shows normalized fuel consumption versus the turbine outlet temperature or the exhaust temperature. The results have been normalized with respect to the baseline. So clearly, baseline has temperatures that are too low to sustain any warm-up or after treatment or stay warm at all. State-of-the-art thermal management has temperatures close to 260 C. And these are achieved by using almost 60% more fuel. Again, these are all steady state results. 3-cylinder CDA has temperatures above 210 to 115 C, and it uses 4% less fuel than the most efficient fuel engine calibration, which is the baseline here. So that, combined with the fact that 3-cylinder CDA has reduced airflow, is what we really like about CDA for a stay warm operation. Looking at the plot at the bottom here, we have normalized engine out soot and engine out Knox, and three-cylinder CDA has significantly low Knox and soot as compared to the state-of-the-art thermal management. Next, let's look at this plot here shows experimental SCR cool down, and it really brings out the capability of three-cylinder CDA to maintain after-treatment temperatures for a longer duration of time at favorable values. So this is experimental data, and we started out with an SCR output temperature of about 330 C, and we just let the engine idle at 800 RPM and 1.3 bar PMEP. And for the two strategies, we see that three-cylinder CDA is able to maintain higher SCR outlet temperatures longer. And the reason for that is obtainable by looking at the equation on the top, which says that the rate of the heat transfer between the exhaust and the SCR catalyst is proportional to the temperature of the exhaust, or the TOT, and the catalyst temperature, and also to the exhaust flow rate. So since CDA has reduced exhaust flow rate and a sufficiently elevated TOT, it is able to minimize this rate of heat transfer to the catalyst. The catalyst is already warm by this point. And that is the reason that it can maintain SCR output temperatures warmer for a longer period of time, all the while having 41% lower fuel consumption than state-of-the-art thermal management. So this is an idling duration of about 25 to 30 minutes, and for most of the portion, CDA has warmer temperatures. This is the key fundamental idea that we use in our transient drive cycle results coming up next. The slide is meant to summarize what I just talked about earlier, so I'll go on to the next one. So here is the HDFTP, the composite cycle with the cold start and the hot soak and the hot start. Over this cycle, we ran state-of-the-art thermal management for the first 600 second idle sections of the cold start. So these are the warm-up idle sections where the SCR is just getting up to temperature from a cold start. And then at the idle sections, after 700 seconds, we ran three-cylinder CDA. So that included some idle sections of the cold start and all the idle sections of the hot start or any subsequent hot starts in a real life. So really, once the 700 second mark is crossed, the SCR temperatures have already reached favorable temperatures by use of the thermal management calibration. And the job of CDA is to maintain those temperatures while also saving fuel. So these are the plots for temperatures that we saw earlier. So these are HDFTP with no CDA. This is just what the engine would do conventionally in terms of the state-of-the-art thermal management. And these are the results for HDFTP with CDA. So up until about 700, 800 seconds of the cold start, the red and the blue line are exactly on top of each other in terms of the temperatures. And that is expected because the engine is running the same calibration during that time. But after 700 seconds, the difference start to build in, and we can really see the advantage of CDA in maintaining temperatures about 400 seconds into the hot start. So throughout the hot start, CDA is able to maintain similar and or higher temperatures than state-of-the-art thermal management. And because it has lower tailpipe, lower engine out Knox, it also will be able to meet the same emission targets as the state-of-the-art thermal management. As a result of that, three-cylinder CDA is able to have 3% lower fuel consumption over the composite FTP than the state-of-the-art thermal management operation. And this is a significant number, and notice how close we are now to the baseline operation while still meeting the desired targets. So next, we identified more sections over the FTP where we could run CDA, and these included loads below 3 bar PMEP, as shown by the brown shadings here. again, a significant portion of the hot start, like a lot of opportunities in the hot start, and some portion of the cold start too. So additionally, that led to almost 0.5% more fuel savings, and we see the green dot on this as a result of the running CDA at all loads below 3 bar BMEP. So looking at this, we are about just 1% more fuel consumption than the baseline operation, while meeting 2010 emission standards, if not doing better on those. So next, I want to talk about the Orange County Transit bus cycle. So this is another example of a real-world drive cycle, and it's based on driving patterns of urban transit buses in LA. It has been developed by West Virginia University, and it includes both urban and highway driving sections. So a key feature of this cycle, again, is that about 70% of the total time is spent below 3 bar BMEP over the entire cycle. And what that means is that the engine is going to use state-of-the-art thermal management throughout this cycle, throughout the day as the bus goes on many trips. So we have opportunities to run CDA here in order to save fuel. So at about after 700 seconds, we consider that the SCR temperatures have warmed up by then, and then we identified sections below 3 bar BMEP where CDA can be run. So if we predicted 5.6% fuel savings over this cycle by running CDA for stay warm during the stay warm operation, and 8.7% fuel savings if CDA was run over the entire cycle. And the 8.7% number is probably more frequent because the transit bus will keep running hot starts for the entire day. So it has the potential to run CDA for the entire cycle as it goes through significant portions of low load operation. The next real-world drive cycle that we looked at was the NRail Portage Composite cycle. This is a very interesting drive cycle that has been developed by NRail based on operation of Class A trucks near the ports of LA and Long Beach. So NRail came up with this cycle based upon a lot of data, about 36,000 miles of real-world data and quite a large number of Class A trucks. And it's interesting that this study, it's not surprising that this study came up from the LA/LB region, considering the non-attainment zones that California has for this. So for the Class A trucks, NRail identified 4 sections where these trucks spend a majority of the total time, fuel, and the miles. As you can see, there are 4 colors here, and each of those colors translate to a certain speed profile. There's the creep Q profile here, which is very low load operation, and that corresponds typically to trucks waiting in line as to unload or to pick up containers. That idling time here is about 1200 seconds of cycle, but it can go as long as up to 2 hours. So again, lots of low load operation. And then there's a port or near dock operation where the trucks are moving locally, are moving close by. And there's a local operation, and then finally the metro highway operation where they are beginning to move inland to actually transport the goods. So the speed profile was developed by NRail, and then we used autonomy to obtain the engine and speed traces corresponding to this, which are seen on this plot here. So here again we see numerous opportunities of running CDA, primarily because there's a lot of low load operation, significantly so in the first portion, which is the creep mode. So over this cycle is almost 100% low load operation below 3 bar BMEP, and we predict 35% reduction in fuel consumption by running CDA over this cycle. So there's the engine will almost entirely be in CDA for about 20 minutes, and will result in significant reductions in CO2 as well as Knox and soot. So the CDA strategy that has been developed at Purdue has engine out Knox levels, which are much below the current certified field idle numbers, which is a great leg up. So over the next section of the composite cycle, which is the port near dock mode, again, there's a lot of low load operation here. So we predict 21% fuel savings by using 3-cylinder CDA over this cycle. 10% fuel savings over the local mode, and about 4% fuel savings at the highway mode. Notice how this highway mode cycle looks very similar to the HDATP cycle. So the 4% number lies close to the 3.4% that we saw with the HDATP. This is by running CDA at all loads below 3 bar PMEP. So to summarize, and significant fuel savings are possible for the entire port rate cycle, which means that the Class A trucks near the ports can save a large amount of fuel by running CDA for most of their operating time. So with that brings me to conclusion slide to summarize what we have seen so far. So the experimental results at loaded idle have shown that 3-cylinder CDA has 41% lower fuel consumption than the state-of-the-art thermal management operation. It has more than 50% reduction in engine out Knox and more than 80% reduction in engine out soot. And the benefit of CDA arises from the fact that it has a sufficiently elevated exhaust temperature and reduced airflow, which allows SCR cool down which allows for slower SCR cool down. And then over the HDATP, we demonstrated experimental results that show 3.4% fuel savings over by running CDA at stay warm portions of the cycle below 3 bar PMEP. Over the Orange County cycle, we've seen 5.6% fuel savings for the first cold start of the day, which is the first trip of the day, and then 8.7% fuel savings are predicted over the hot starts, which would be the trips for the rest of the day. And then over the port rate cycle, the composite port rate cycle, there are significant fuel savings possible on the creep mode, which is 35%, and all the way and up to 4% possible on the highway mode. Just a few additional comments before we start taking questions. Considering that the SCR system in our test cell is not a closed couple system, but by the use of a closed couple SCR system, the benefits of CDA can be very interesting. Secondly, due to lower NOx and soot that we see with CDA, they can have positive implications for affecting DPF region frequency and the fuel consumption associated with it. And on account of the lower NOx, also the DEF consumption. But these are projections and not studies carried out at Purdue. With that, I would like to acknowledge our research collaborators from Cummins and Eaton, Dr. Eric Holloway, project manager at Purdue for the VBA project, and the shop staff at Herrick Labs. So thank you very much, and we'll take some questions now.
Yeah, thanks, Mirinal. Great stuff right there. I can see why the paper and the presentation was so well received. So now is your opportunity as the audience to engage our experts. So please send us questions. Some of you already have, and we appreciate that. We'll get to as many that we have time for, and we have about 20 minutes left here. So looks like we've got a few questions coming in. So let's go ahead and get started here. So I think I'm going to start out with this question to you, Mirinal. How smooth was the transition from CDA to normal mode across the transient drive cycles that you shared today?
Right. The transients there has been a CDA transiting study from Purdue, and a paper is available for that. The transition from CDA to six-cylinder and six-cylinder CDA is not at all noticeable on the engine, and I would say it's a very smooth transition with three-cylinder operation.
Okay. We've got one for Dr. Johnson here. John, how much new technology for diesels will be needed to meet the 2027 NOx and CO2 standards?
Okay. I'll give you a little bit the length of time that I've been in the diesel industry. Early 1960s, I was at International Harvester, which is now Navistar, and there were a lot of naturally aspirated engines, and turbocharging was coming in, and with some in intercooling. So I've got a long history of seeing the technology change. There's always a need for new technologies. I think sensors. There needs to be algorithms. I think that there will be a lot more model-based control of the system. We need to integrate the after-treatment systems, cooling system, the fuel systems, a lot of electrification too, and we need to meet the standards and also control so that in actual driving we can meet low emissions and also really good fuel consumption, because the cycles, the certification don't always match exactly what happens in the field. There needs to be a lot of reliability and durability, and obviously these systems have to be low cost. So there is a need to do a lot of R&D, both in the field and in the laboratory, to develop these very complex systems that will be needed, I think, in the future.
Okay. Thanks, John. I appreciate that. Greg, I think this might be one that you could handle for us here. So when using CDA, what drives the increase in fuel efficiency while driving down both engine out NOx and particulate?
Yeah, I'm happy to tackle that question, Tony. In broad strokes, what we've seen across a variety of speeds and loads of operating cylinder deactivation for fuel efficient stay warm operation, the after treatment, what we've seen in all those cases is that the primary driver for reducing fuel consumption is allowing the engine to breathe less air. As we breathe less air, that pumping loop gets smaller that Dr. Joshi talked about. That then drives a fairly significant reduction in the fuel flow. So we reduce airflow effectively to reduce fuel flow. And when we do that, the air-to-fuel ratio decreases a little bit. So maybe if we were at 35-to-1 air-to-fuel ratio, now we're at 30-to-1. So we're not starving the engine of air. The air-to-fuel ratio is coming down a little bit, but the fuel consumption is coming down by almost as much as is our reduction in airflow. So what does that mean? It means we save fuel. It means that we're able to maintain similar exhaust temperatures coming out of the turbine as we were with the state-of-the-art thermal management strategy that Dr. Joshi talked about. And we're putting less air and fuel in the engine. And we're doing so in fewer cylinders. In the case that she was describing here today, 3 cylinders instead of 6. So our air-to-fuel ratio is still elevated, which helps us with soot in general. We're also putting less fuel in the cylinders on total, and our EGR fractions are still essentially where they were before we did cylinder deactivation. So we're not doing anything to compromise the engine out emissions. In fact, because we're putting less fuel in the engine, we're generating less emissions during the combustion process, and that's why you see, these 50 to 60% decreases in both soot and PM coming out of the engine in this mode, while we simultaneously keep temperature up and fuel consumption down. So it really is, it is the best, or one of the better ways, if not the best way, to operate a diesel engine at low to moderate loads anyway. It just so happens that it also helps us with the after treatment.
Great. Jim, we've got one for you here. So it's a bit of a statement and then a question. So CDA adds cost to the engine. Have you guys investigated the payback time in terms of fuel savings?
Yeah, that's a great question. And anytime you look at new technology, you're going to add some costs. But the real issue is what does it enable? So you're going to enable the existing after treatment system to work better. And Dr. Joshi talked about all the fuel savings. So every OEM is going to have their different way of looking at payback. And a lot of that's due to fuel or on cost. So can you go ahead and use existing after treatment systems, or can you downsize it because you have better heat management using CDA? So that's one element. What can you do with the onset cost? And the other thing is fuel savings. And then it's really over the drive cycles for payback. And I think those numbers are going to be maintained by the OEMs with their different drive cycles. So it's a great question, and it depends as always. But with the fuel savings that Mirinal showed today of 4% on highway and up to 35% in drayage operation, the game gets real exciting.
Sure. Mirinal, I've got a couple of NVH questions for you here. So did you encounter any NVH issues in your engine test cell while using CDA? And maybe an add-on to that have you investigated the vibration implications of running CDA in vehicles? And if so, what have you learned?
To answer your first question, Tony, no, we have not seen any NVH issues when we ran 3-cylinder CDA on the engine. I don't think I have sufficient data to answer the vehicle NVH-related questions right now.
Okay.
Because that's not
because this was strictly in the test cell, what you spoke about today, right?
That's right. But there have been studies carried out at Purdue itself to address in case any NVH issues were to arise because of some strategy. There have been studies carried out at Purdue to resolve those, and there's publication available on that. I'm talking about dynamic CDAs. Mm-hmm.
Right.
Tom, a few weeks ago we had Tom Reinhardt on, and he talked about how NVH could be managed over real truck cycles. So I think maybe some of those answers are in Tom's presentation from a previous webinar.
And we'll make sure we get those up onto Eaton.com as well. So thanks for the reminder, Jim. Dr. Johnson, another question about technology and maybe future technology here. So in your opinion, does meeting the future standards involve system integrations of technology that already exist, or is it going to require entirely new inventions?
Well, I think it rests heavily on system integration of the basic engine, the after treatment system, and the cooling system. And with a powerful ECU along with sensors and the control system to manage the system on both the cycles for certification and also in the field under actual driving conditions. We always can use new inventions, and we think our patent that I told you about before is a new invention, and sometimes inventions take a long time to actually get into practice. So it's probably pretty much all of the technologies that are available now, because we're getting fairly short relative to 2024 and 2027. So that's sort of it. We need a lot of sensors, I think, and there are going to be more sensors and more algorithms to do all of the controls and new thinking. We've published several papers on our estimator as a way to use sensors and everything and model-based control to really manage the after-treatment system. So it does involve integration, and we can always use new inventions, but new inventions take a while to get into actual practice.
Sure. Greg, here's one for you. What opportunities do you see for reducing NOx and CO2 simultaneously for non-road engines?
Well, Tony, I think it's significant there too. And I from what I understand, and I'm smiling as I say this, we know the customers off-road also care a great deal about, saving fuel, as do those that are on road, right? So just from a fuel savings standpoint alone, cylinder deactivation, as Dr. Joshi has kind of stepped through here today, has a significant opportunity. Certainly when and as vehicles off-road are idling or going through lower load operating strategies. And some machines are more prone to do that. Some machines are less prone to do that, right? So a combine harvesting grain is high load operation, and you're not likely going to be operating CDA unless you bring that vehicle to a standstill and you idle. And then you would want to, then CDA would be a great way to save fuel and keep the after treatment warm. So even in that case, it would have some benefit. So I think that what we've learned here about the physics, what Mother Nature's teaching us, and the basic physics and the interaction of the engine and the after treatment, these things hold true for the off-road vehicles as well. And I think the benefits are for both on and off highway are also around what you have to do at the engine to maintain temperature of the after treatment. The strategies used today put a lot of stress on the engine. Late injections, gas exchange where you're putting back pressure on the engine. For both on and off highway engines, there are components in the system that are you're leaning on that you wouldn't have to lean on as hard during cylinder deactivation, and that's true both off highway and on highway. And what I understand from my industry collaborators is, uptime, keeping the machine operating as expected, is a big deal for off highway applications and on highway applications. So, we want to reduce Knox, we want to reduce soot, we want to reduce fuel consumption, but we also want these engine systems to be available for their purpose more frequently. And so if we can lean on some technology less as we keep the after treatment hot, that's a good thing too for both on and off highway. So I just thought I'd throw that in there as well. Thank you for the question.
No, that's good. No, thank you. We've got a couple more questions in the queue here, so we've got a few more minutes. So please, if you haven't asked a question, you've got a perfect opportunity here for our experts. So, Jim, we've got one for you here. So, it appears that a significant amount of time is spent below 3 bar BMEP on these cycles, and that resulted in huge fuel savings: 8.7, 35% on drayage. How did your research group find this 3 bar BMEP limit, and is there a technical reason that it was chosen?
Yeah, that's a great question. And in fact, when we first started working on CDA, we thought we could go up to half engine load, because if you're just deactivating half the cylinders, you could run each of the firing cylinders at full load. Now, we found out we needed to back off on that, and we did a lot of work at Purdue. And then we built the demonstrator engine at Eaton and Marshall, and we really looked at this, and we just ratcheted up load, and we were looking at two metrics. We were looking at exhaust temperature and fuel savings. And what we found is above 3 bar, we were already at temperature. So the real benefit of CDA is to get the temperature where it needs to be. And then we saw that the fuel consumption crossed over somewhere around 3.5 bar. So if we went above 3.5 bar, we had more temperature than we needed, and we started hurting ourselves in fuel. So we found this happy medium of, hey, at 3 bar is really our crossover point for temperature and fuel savings. And we fed that back to our collaboration, and then we kind of, and that's where we really took off and really started seeing some of the results that you're showing here. But really finding that sweet spot was really key in uncovering, what we could do with temperature and fuel savings. Thanks for the question.
Sure.
Tony, can I jump in on that one too?
Yeah, sure. Go ahead.
I agree 100%. I agree with 100% with Jim. For on-highway engines, that typically operate, say, at a lower speed than, say, an off-highway engine, a diesel engine might operate. I think this is there's some speed dependency here. So for off-highway engines, for instance, operating in that combine, that engine in general is operating at high power, higher speeds, per my understanding, than an on-highway engine may be made to operate with the way the transmission runs and, say, a heavy truck, Class A truck operating mode. As you go to higher speeds, say for something like a 15 or 13 liter engine, above the 1200 to 300 RPM, if you operate your engine to higher speed, then the benefits of CDA, I think, will be even higher than 3 bar, maybe 4.5 to 5 bar. We got our head wrapped around that with Eaton in our work with them. But I agree that for on-highway engines, kind of the place you want to operate CDA is up to around 3 to 3.5 bar. But for the off-highway applications, high-power applications, you may even want to operate CDA to higher loads if and as those engines are operated at higher speeds than is typical for an on-highway application. So thanks.
Great. No, thanks for adding on to that. Myrnal, we're going to give you the last question as the keynote speaker here. So bring us home with this one. What is the fundamental reason that fuel savings using CDA increases so dramatically from the metro highway operations where we saw 4% to the port near dock at 21% and then the creep mode at 35%?
Right. Thanks, Tony. So the fundamental reason is that as we move from right to left on that port rate cycle, the amount of time spent at loaded idle, amount of time spent below 3 bar VMEP is increasing significantly. So the closer we get to operating at low to moderate loads for a large portion of time, the more opportunities we have to run CDA to keep the aftertreatment system warm. And that's where the crux of CDA is, of course.
Great, thank you. So we appreciate everyone's questions that came in. Lots of good discussion. The audience really liked the presentation here, Dr. Joshi, and the rest of our panelists. I want to thank our panel of experts for sharing their knowledge on diesel CDA. I also want to remind you that we have additional webinars coming up, and that is next week on October the 21st and then October the 28th. So Dr. Greg Shaver, one of our panelists today, is going to be our keynote speaker next week, and he's going to talk about understanding diesel cylinder deactivation. And then on October the 28th, Dr. Cody Allen from the University of Illinois is going to talk to us about cylinder deactivation versus cylinder cutout, and what are the differences between those two technologies. So be on the lookout for emails and social media announcements, and we hope that you join us as we delve deeper into diesel cylinder deactivation. Thank you for watching, and everyone have a good day.